In this video, I will introduce our work, online vectorized HD map construction using geometry. Two keywords of the task are online and vectorized. Online means taking sensor data, such as camera images or lidar point clouds, as input, and directly constructing HD maps. The vectorized format of HD maps has been widely adopted in many downstream tasks, such as trajectory forecasting or planning. In our work, we notice a neglected property of map instances, geometry. One example of geometric properties is the shape of the highlighted pedestrian crossing. As the ego vehicle turns right or moves forward, the shape of the crossing remains unchanged. However, the vanilla representations of vectorized HD maps utilize absolute coordinates. With the movement of the ego vehicle, the absolute coordinates change a lot, which means the representations are sensitive to rotations and translations. Here is a real case. The baseline model predicts distorted pedestrian crossing in a tilted scene. Moreover, the HD map consists of different types of instances and has various geometric properties. Without distinguishing the difference in geometric properties, vanilla point-centered attention struggles to effectively learn shape and relation geometry, as shown in the figure. How to solve the problems? Let's first focus on points and displacement vectors. Our plain idea is that the patterns of local clues can reflect the shapes or relations of instances. We use the angles between displacement vectors and the distances between points. Combining these local clues of each instance point, we obtain the geometric representation. Under our geometric representation, a rectangular instance with 4 vertices can be formulated by a 90-degree angle and 2 pairs of equal sides. Similarly, a straight line can be represented by all the angles equal to 0 or 180 degrees. Moreover, we also distinguish 2 different types of geometric properties: the shape of a single instance, shown as a rectangle, a straight line, etc., and a relation between different instances, including parallelism, perpendicular, a certain lane width, etc. Thanks to the relative property of angles and distances, under rotations and translations, our geometric representation remains unchanged. Build on top of such geometric representation, we propose the GEMAP method. This method first consists of 2 Euclidean loss functions. One is the shape loss, and the other is the relation loss. To optimize geometric representations, we calculate the geometric representations of predictions and labels and define the corresponding loss as the L1 norm distance between them. In addition, since there are 2 different geometric properties, shape and relation, we also adjust the attention module to form geometry decoupled attention. We use shape attention between points within a single instance and relation attention between points of different instances. Decoupling these 2 kinds of attention is more conducive to the learning of various geometric properties. We conduct experiments on the NU scenes dataset and obtain state-of-the-art result. With extra lidar input, our method can enjoy an extra bonus. On the RGovers2 dataset, our method also shows extraordinary performances. To evaluate the effectiveness of the proposed modules, we do ablation studies on the NU scenes dataset. The GDA can obviously increase baseline performance. However, only adopting geometric loss might be a bad idea. Only by cooperating with the proposed GDA, the geometric loss can exert its power. Here is a short comparison video between GEMAP and the baseline model. In the first clip, the raindrops occlude the front windshield, and the baseline model fails to recover the occluded boundary. However, our GEMAP can avoid this problem. The next parts present another 2 driving clips which include heavy rotation or occlusion, and our method can reach a better result. As you can see, when the ego vehicle turns left, GEMAP avoids missing a large amount of instances. In this clip, the pedestrian crossing in complex shape is heavily occluded by the truck at first and later by the black car. GEMAP can better perceive the shape under the later condition. In conclusion, the contributions of our work can be summarized as follows. First, we explore the application of geometric properties in online vectorized HD map construction. Second, we propose the GEMAP method, including the Euclidean loss and geometry decoupled attention. Finally, enormous experiments are conducted and the best results are achieved. Moreover, the visualization results also support the robustness of our method to rotations and occlusions. Thanks for your listening.